Hi everyone, really glad to be here. My name is Maman. I'm a postdoc at Audio Labs Erlangen, a group of Meinrad Moller. I did my PhD at Tel Aviv University. I will talk today about multi-aspect conditioning for diffusion-based music synthesis. So what is conditioning in the context of diffusion models and generative models in general? So if we have a generative model that generates images, conditioning means we want to not just sample a random image, but rather sample an image for a specific class. For example, the class of lions, so generate random images of lions. So this is conditioning for diffusion models. And in our context, we apply two types of conditioning at the same time. So one is what we call musical score conditioning. So we want to sample out of the class of musical performances that have a specific musical score. And the other is what we call version conditioning. These are meta level or global characteristics that we would like to emulate. So I will start with a demo, and we'll show these two different aspects that we condition on. Okay, so I will play the input to the model. Our input is a MIDI file representing the musical score. I can synthesize it with the media player. This is what it sounds like. Okay, and this was the input, and now we learn how to render performances and get realistic sound. Learn this from real data. This is what we generate. Another example. This was the input, and this is what we generate. Baroque style with harpsichord and strings. Okay, or this is famous. Okay, so what our input is simple MIDI, so it's semitone resolution, and there are a lot of nuances of performance that are not represented in the MIDI. For example, if we have a violin playing, we have fluctuations in pitch, expressive fluctuation in pitch. This is not represented in the input, and this has to be generated by the model. So here's an example. This is generated. and we can have a really wide variety of instruments. So we can have, for example, strings, wind, piano at the same time. So this demonstrated our musical score conditioning. So we have a MIDI input, and we see that we can get realistic, pretty convincing sound. Now let's understand the other type of condition, which is the version condition. This is conditioning on global meta-level aspects like acoustics. So let's start with a simple scenario. We provide our model a MIDI without any instrument information, just pitch. So we play it on a simple synthetic piano. Okay, and now let's render it according to different versions. I'll play examples from each version. Okay, so we have orchestra. This is a harpsichord. Violin. It sounds like one violin. Okay, piano. Okay, so let's render it according to each of the versions. Okay. Piano and violin. Okay, I have another example. This is the input. And now, first version. Second version. Okay, let's play this one. Play again so we hear the differences. Okay. Okay, and we had wind. Okay, so we hear that the basic concept of instrument timbre is captured by the version. So we provided the model just pitch only MIDI, and the version and the model captures the instrument that appears in the version. Okay, very nice. Let's take a more kind of complicated case. Let's say we have two different church organs. Okay, let's play two samples. This is real, real recording. And this is another church organ. Okay, you can hear that these are, although both of them are called a church organ, they are really different. One has this flute-like sound, right? And the version condition enables us to distinguish between different instances of the same instrument. So we can provide MIDI that says also the instrument, asks for a church organ. And with the version condition control, exactly which acoustics we want. So this is the first one. So this is the capability of the version condition. We can do also rock songs. So this is Bee Gees in the style of Guns N' Roses. This is the input. And now let's play it, render it in the style of Guns N' Roses. So this is instrumental music. You might ask what happens with singing. Using a similar approach, we can do singing voice conversion. So this is Source from the Beatles.
What would you think if I sang out a tune? Would you stand up and walk out?
And now let's render it in the voice of Jim Morrison. This is a reference sample.
Consciousness, I'd like to have another. Think if I sang at it? What would you think if I sang at a tune? Would you stand up and walk out on me? Lend me your reason, I'll sing you a song, and I'll try not to sing out of key. While I get by with a little help from my friend.
And the style of Dietrich Fischer-Dieskau. He's a singer of classical romantic music. Now we have recordings of him in German, but we can make him sing in English.
What would you think if I sang that it's me? Would you stand up and walk out me? Let me your ears and I'll sing you a song, and I'll try not to sing out of key. I get by with a little help from my friend.
And now last thing, can we do both of them together? So we did MIDI to audio and we did voice conversion. Can we kind of take the mixture of instrumentals and vocals and convert them from one performer to another? So this, the answer is yes, using this approach. So let's generate Riders on the Storm in the style of, this is generated but conditioned on the original singer, the Doors, Jim Morrison from the Doors.
Let your children play. If you was better right, sweet, where you will die. You're on the road. Yeah.
Now let's hear it in the style of this Dietrich Fischer-Dieskau.
Let your children play. If it on this little right, sweet, better we will die. Girl on the road.
Or Creedence Clearwater. So this version conditioning kind of captures all the different global characteristics. So it captures the singer identity, and also if we have a special unique guitar that's characteristic of the performer, this is also somehow captured by the version condition. Okay, so this was a demonstration. Now let's talk about technically how do we do this. Okay, so a little bit about musical representations. We have can order them from signal level to more semantic or abstract. We have waveform, STFT, MEL spectrogram. Then we have MIDI, which is still in the physical time. MIDI is already symbolic semantic. We talk about notes and instruments, but the time is physical. And then we have sheet music, which is even more abstract. The time is musical, so we can interpret the time differently. Now, MIDI, in principle, is just a list of commands for a sequencer to parse and perform. It's also equivalent to a piano roll, a matrix of time over pitch class. What we will talk about today is transcription, and I will talk a little bit about transcription because it is important for synthesis. So transcription is going from audio to MIDI, and synthesis is going from MIDI to audio. This is in our context. Some would say transcription is going from audio to sheet music. Yeah, maybe, but this can be done by another model that goes from MIDI to sheet music. This is already a pretty, not such a trivial problem. So in our context, transcription is audio to MIDI, and synthesis is MIDI to audio. What are the challenges in music transcription? So first of all, we have partials and fundamentals. We want to detect only the fundamental frequencies, eliminate the partials. If we have a monophonic signal, only one voice at a time, this can be done even without machine learning with pretty good accuracy. But when you have polyphonic music, multiple sources at the same time, even multiple notes at the same time, you have a mixture of fundamentals and partials, and this already becomes complex to distinguish which is fundamental and which is not. And after we detected the fundamental frequencies, if we want to do transcription, we have the concept of notes. Notes have a beginning and end. So we would have to detect what time exactly does each note start and end. This is the beginning of the note is called the onset. The end is called the offset. Now, in music synthesis, we go in the other direction. We have a musical score as a MIDI, and we want to synthesize the audio. Now, we have concatenative basic synthesizers. Right? We have the Windows Media Player synthesizer. We know the correlation between pitch and frequency, so we can always create these sinusoids and sonify a musical score, but the thing is that this will not sound realistic. And now we ask, what makes realistic sound, right? So I would say expressive performance nuances. So expressive fluctuation in pitch, or this is called vibrato or tremolo. Expressive fluctuation in the intensity, in the volume. So these aspects of performance are hard to generate. We also, I would say, another challenge: how do we emulate the timbre of a specific instrument that we hear in a specific recording? Right? We would like to have the ability to really emulate the specific guitar that we like in a certain recording from, 1976, right? So these are challenges that are not addressed by the basic synthesizers. Now, a little bit about transcription. It's something that we actually really rely on for music synthesis. So I'll play some samples. We have an audio recording from YouTube. And using our approach, this is work that I did during my PhD. We transcribe it into MIDI. Okay, or if we don't know the instrument, we can do a pitch-only transcription. Okay, so how do we get data for this transcription task? This is really an issue. So for piano, we have what's called this clavier. You can see there's a ghost playing the piano, right? So this is a special machine that enables us to both record MIDIs from performance on acoustic pianos, or the other way around. We can provide it a MIDI and it can play it on this acoustic device. We can get a lot of data really accurate. Okay, so this has led to the development of onsets and frames model. This was really kind of a breakthrough in piano transcription. So the idea was, instead of the common approach was to detect note activation, whether a note is active or not at each time frame. But their insight was it's more important to detect the note onsets, the beginnings of the notes. So this is the main focus. We have an onset head that detects a convolutional and LSTM, detects the note onsets, and then we have an auxiliary head, complementary component that predicts the note duration. And this already gave this model, after some development, gave about 95% accuracy on piano transcriptions of transcription of Beethoven piano sonatas, which is it is really robust. But for other instruments, we do not have this kind of machine. The only thing we have, which is not easy to work with, we have recordings of classical music that follow a well-known musical score. So we can take a MIDI performance of Beethoven's Fifth Symphony, and then we have a lot of different real performances of this. But this is really not aligned. They come from different sources. If you take some naive approach, even try to align with DTW, this will not give you labels that are good enough for training. But what we proposed in this work was to use activations from an existing neural network, pre-trained neural network, as features to align musical score to new audio performances, and get, using the network, you get training labels. So we start with some domain where we do have accurate data, like even synthetic data, multi-instrument synthetic data. We train a transcriber on this data. We get a weak transcriber. Why is it weak? Because of the domain gap was trained on synthetic, for example, and then we want to apply it on real performances. Performance of this model will be weak, but it turns out that these features are really good for alignment. So if we have new data where we have pairs of audio and really unaligned musical score, we can use the features from this model, apply it on the new audio, and align the score to the audio and get automatically training labels. And now we can adapt our model to this new domain. Now the key insight in the alignment is the onset features. So the best features for alignment, in this case for transcription, for onset-based transcription, is using the onset features. So you could do something like a coarse alignment using DTW, where you can also use the neural features. But then the really important step is local maximum adjustment. So we know from the DTW some area where a node should occur, but if we really want to get the exact timing, so we get a useful training label, we use some estimate of the error, temporal error. We have this window around this estimated time, and then we pick the time with the highest likelihood according to the posterogram that we have from the pre-trained model, and we get really good labels. You could also even discard the DTW and just do this peak picking. You can take histogram information and then use the posterogram to locate the top K likely timings. So this we presented, the histogram paper we presented recently in Izmir. So we start with synthetic. We do alignment of real data to audio and score. We train, and then we can also repeat the process. Maybe our transcriber now is better and can give us better alignment. Okay, just a comparison with a Google model. Okay, so this was a real recording, and now this was the state-of-the-art and multi-instrument transcription, a model by Magenta. Now, the problem is not necessarily with the model, but with the data. It used data where the alignment was bad. No? And this is what we produce. Now we start sounding like Magenta. Not good. Yeah. There are more samples on the website. Okay, let's play one more. This is what we transcribe. This is, okay, I will skip this. This is using histogram supervision. So this was transcription, and just quantitative results. If we compare to the Magenta model on multi-instrument transcription, we get cross dataset evaluation. So we train on datasets other than Maestro and evaluate on Maestro. So the Magenta model gave something like 28%, and we get something like 90 because of the using a much more effective alignment technique. And we can see on the MAPS data set, we are, even though our method is weakly supervised, we get performance that is slightly higher than supervised on the MAPS data set. And why? I would say probably because of the more diverse training data. So our method enables to train on recordings from really diverse sources. It is better for generalization. Model trained on Maestro applied to MAPS gets 86. We train on MusicNet, which has a lot of piano recordings from different sources. We get performance that is slightly better. We released a new version of the MusicNet dataset with refined labels. So there you have string and wind instrument. So this was transcription. Let's get back to music synthesis. So as I mentioned, we have score condition and a version condition. Score condition has the notes and instrument. Version has all these high-level aspects, identity of the performer, the style, acoustics, maybe in the recording environment. So using this approach, if we have a bank of recordings, we have, for example, Toscanini playing Beethoven's Fifth Symphony, and using our model, we can now take some musical score of a new piece, Brahms' Fourth Symphony, and render it with the style and acoustics that we hear in Toscanini's recording, and then we get Toscanini conducting Brahms' Fourth Symphony. This is the idea here. What we do is generate MEL spectrograms, and then in order to convert the MEL spectrogram to a waveform, we use an off-the-shelf vocoder. Going from MEL to audio with high quality, robustly across domains is really not trivial at all, but there are models that do this decently. At the time there was SoundStream, today there's Big Vegan, and there are also like VAE techniques, right, audio coding kind of techniques. A bit about diffusion models. I mean, probably you know. So we have a process that goes from signal into noise. So at each step, we have a signal. Each diffusion step, our signal can be represented as a weighted sum between the original signal and noise. Or equivalently, this can be represented as a Markov chain, repeatedly applying noise. But for training and practice, the first approach of having this weighted sum is much simpler, and this is already similar to the way flow matching works. Now, a key tool that we use here is the film layer. So the version conditioning is all done through what is called film layers. What are film layers? This is a conditioning mechanism that enables us to train many in one model. So if we have a lot of different tasks, we want our model to perform, train a model to do at the same time. These tasks are somehow connected, but not exactly the same. We can use this mechanism. So first example is diffusion itself, right? We train a model to denoise with varying noise levels. So each noise level, if you think about it, is a distinct, different task, right? So the handling of different noise levels in diffusion models is done through film layers. And what the film layer does is it learns affine transformation, an affine transformation per network block. So for each block of the network, we multiply by a constant and add a constant. It's a constant across time, and this depends on our conditions. So we can, in a restricted way, modify our features at each block depending on the mode or the task. So this is in diffusion the noise level, and we extend this mechanism to support the version conditioning. So if we have two guitars, so each block, two different guitars at each block of the network, the denoising is done a bit differently according to the guitar, but the modification is restricted. It's in affine, only in affine transformation. So if you want to know technically, you can take, if you have two different conditions, noise level and version acoustics, you can concatenate the representations, and then you get an affine transformation that depends on both at the same time. So we have a set of audio recordings, different instruments, different performers, and we train our model to denoise MEL spectrograms conditioned on the version and on the musical score. And then at inference time, if we want to generate, because of memory constraints, we can only work in training with 5-second segments. We want to generate something performance of 10 minutes. So how do we do this? We do overlap synthesis. So at inference time, we take the segments that have overlap and then smoothly interpolate. I'll explain this at the end. Now, challenges. Let's talk about the challenges and also define our goals in light of these challenges. So, of course, this is a very ill-posed task, right? So, let's say we decided that we want to hear a violin, but there are many different violins in many different acoustic environments. So, which one? This is ill-posed. Even if we decided on the exact setting, the violin and everything, we can have style variation. The same person can play the same piece in many different ways. So we have to somehow model this variation, and there is also a technical challenge, which is how do we get training data, but I already hinted at this. We have a good, robust transcription algorithm that can work on data in the wild, and we rely on this. Okay, so our goals are to synthesize performance as realistic as possible, ideally indistinguishable from real performances. We want to have control over the musical score, which includes the notes, instruments, and timing, and we want to have control over the meta-level aspects, acoustics, timbre, and general style. Now, for the first aspect, for realism, the key ingredient here is to train on real data. So previous work, because of the lack of data, just took data from a simple concatenated synthesizer, and then you train a diffusion model to learn to imitate a concatenated synthesizer, and you do not leverage the full expressive power of the diffusion model. It's kind of missing the point, right? So the whole point of diffusion models is that they can learn to imitate, sample from the distribution of real data. So we use real data, but then we have the data challenge, the technical challenge. How we need corresponding musical scores that are well aligned. And for this, we use the transcription algorithm from the previous work. So just by training on real data with this automatic musical score conditioning, we get a really significant boost in realism. And lastly, for the version condition, we have the film mechanism. So this way we can handle different instruments within one model, and also different instances of the same instrument, different guitars, different church organs, and so on. And the architecture we use is a encoder-decoder transformer. This was a similar architecture to previous work, but we added version conditioning here and used the transcription as conditioning. These are the two improvements that we made here. So we have a decoder, a spectral decoder, which receives noisy spectrograms and predicts the noise. So it decodes the noisy spectrogram. It's fully attention-based. And we have the film layers that condition on the version and the diffusion time step condition the decoder. And then to condition on the musical score, we have an auxiliary input that comes through a transformer encoder. It learns some representation encoding of the musical score that through cross-attention layers goes into the decoder, and the presentation is learned implicitly in a way that it helps the decoder denoise. So this part, the decoder does the generation process, the decoding. This is the generative backbone, and this is the encoder. This processes the different conditions. time-varying conditions like the musical score. If we want to generate long performances, as I started mentioning before, we do overlap synthesis. So we take 5 seconds and then we start the next 5 seconds a bit before, so there is an overlap. And then at each step of the sampling process, we update this overlapping region to be a smooth interpolation between the output of the model from the two segments. And we do this we don't interpolate the noise, we interpolate the estimated X0, the estimated spectrogram at each denoising step. So we have a deep blending of consecutive segments. Okay, so how do we evaluate this? So first of all, we want to know that we have realistic sound, right? So this is, it has to sound realistic and natural. We want to measure acoustic style control, so how much does our model adhere to our version condition, and we want to measure how much our model adheres to the musical score that we provided. So this becomes pretty complex to evaluate. You have a lot of different aspects. You have multiple conditions. You have to check that each condition is doing something, and of course you want to have a output that is realistic as possible. So for realism and naturalness, we did some listening tests, and we did a mushroom listening test comparing concatenated synthesis models, also comparing a magenta model. We compared conditional and unconditional conditioning on the version or not. So we see that if we condition on the version or not, this does not give a big difference in realism. So even if we don't condition on a specific version, we still get realistic output. So we see this green Google model is the same transformer architecture, but trained on concatenated synthesis data, right? So you get goes from like 30 to 50 by just switching from synthetic to real data. We see that we still have room for improvement compared to reference, even the vocoded version. We did another listening test to measure the effect of the version condition, the style control. So we generate the same excerpt with a target version, and we also generate it with a randomly sampled other target version of the same ensemble. And we asked the listeners to rate the similarity to some examples from the target version. And we see here that there is a big difference. So the version conditioning really creates similarity to our target version. Now, if we want to evaluate musical score control, we can use, we could do some listening tests, but we can also use transcription metrics, right? We have a transcriber that created the conditions for generation. We can also use the same transcriber to measure how much what we generate matches the input. So we have for this standard transcription metrics. So we also complemented the evaluation with Fréchet audio distance, a quantitative measure of quality. So we apply it in two ways. So we can, in order to measure realism, general realism and naturalness, we can measure the distance between everything that we generate and the entire train set or an entire big new reference set. So this would measure how much we deviate from real performances. But we can also do this, so we do this, but we can also do the measure Fréchet distance over subsets corresponding to performers. So we synthesize with the style, with the condition of Toscanini, and then we can measure the Fréchet audio distance between what we generate with Toscanini condition and all the recordings of Toscanini. So this measures how much we are similar to the specific recordings that we want to imitate. Now we use embeddings from the Trill model. So just as a toy experiment to see, does the Trill model capture this notion of version? So we can see here each color corresponds to one version, and each point corresponds to an audio track. So if we look at Hilary Hahn performances of Bach violin partitas, all the audio tracks are clustered in this area. All the audio tracks of this performance are clustered in one area. And if we look at Mitsuko Uchida, Beethoven piano concertos, the pink one, all the audio tracks are concentrated up there. So the Trill model really can capture this notion of version. It maps audio tracks from the same source to clusters. It was trained with this objective, with a contrastive learning objective that should map segments that are close in time to be close in the embedding space, but it was trained only on speech data, but it can still do this clustering on musical data. So now we see a significant improvement of the FAD on the version level, but we also do a further experiment of classification. So for each generated performance, if it's generated with a specific version condition, we then use nearest neighbor, Euclidean. We use the Fréchet distance nearest neighbor, and we look for the version from our train set that is closest to what we generate, and this is our classification, right? So we classify our generated performances according to the Fréchet audio distance, and we see that when we do not use version conditioning, we have top 1, 3, 5 is 16, 31, 41, right? And by applying the version conditioning, the nearest neighbor becomes exactly the target version. We get top 166. So this is an increase of 30 to 50% in the classification accuracy. So this version conditioning is really doing something. Yeah, that's it.
Questions? Yeah, for the pitch transcription, I saw that you compare with, I mean, maybe it's because the work is a little bit, it's not recent, but I saw that the compared baselines are kind of 2020, 2019.
Yeah, okay, but they're...
Compared with the newest stuff, like Spotify's Basic Pitch or Pesto.
So basic pitch and Pesto, they do. Okay, Pesto does monophonic.
I think there's a new one, but yeah, it's true that Pesto is monophonic.
Yeah, they do multi pitch. Also F0 estimation. Usually, okay, there are two kinds of tasks. Right? So usually in F0 you have 5 bins per semitone, right? It's a different resolution, and it's detecting the activation, not the onset, right? Our transcription here is onset oriented, right? It's note level, right? So these are kind of different things.
The first volume of the
but I do not know of like that basic pitch. I think this is still surpasses what.
Yeah, basically it was never.
Yeah. So like this is so in the histogram paper was recent in the last Izmir. So to the best of my knowledge, going from training on data like MusicNet, right, and then evaluating on Maestro and so on, this is pretty much the state of the art. There's some new work from Queen Mary Lab by Xavier Riley. He followed a pretty similar approach. Then instead of going from synthetic to real, he goes from piano to guitar. And there he also, so in this scenario, training with weakly supervised labels and then evaluating in cross data set, you would get like something between 85 to, I don't know, 94, 93, something like that. This is pretty much the state of the art today. So this is, the state of the art today is not much better than this.
Okay, I have a question too. You mentioned that you have performance embeddings. They act as speaker embeddings for speech voice conversion. They're the same thing? But
Yes, so at the beginning, we used just one-hot encodings of the performer, but then we used trill embeddings also for conditioning. And for the speech, the singing and speech voice conversion, yes, we use trill. So we actually use a concatenation of both. So we can do one-hot or embedding, and we apply dropout so it can handle either.
So if you want to condition performances that were not originally...
Yeah, there are some samples. Yeah, let's hear. This is interesting, actually. If there's time.
Yeah, a little bit. We're just a little bit in a hurry, so...
Yeah. Okay.
No, show the example and then we can
Okay.
go to the next presentation.
So this is conditioning on unseen version. So this is our input. Okay, so version number 1. And now, okay, another version. Now we generate this. So it works to some extent on unseen performances.
Let's think. In the end.